I'm a third-year PhD student in Queen Mary. Today, I'm going to talk about my recent topic, fine-tuning disruptor edit Readout, which builds on top of a well-known editing method called MEMATE. Our core question is, once we successfully edit a fact into a large language model, can this edit actually survive when the model is later fine-tuned? If not, how can we improve its robustness? And here's a quick roadmap of today's talk. We have 4 main sections. First, I'll give some background on MEMATE, how it edits knowledge in large language models. And second, I'll introduce the fine-tune robustness problem. The observation that MEMATE edits don't always stick after fine-tuning. And third, I will explain why fine-tuning hurts the edit. And finally, I will share a solution to alleviate this problem. And let's start with the motivation for the knowledge editing. Large language models encode a vast amount of factual knowledge directly in their weights during pre-training, but facts change over time. A classic example is before 2025, the correct answer to who is the president of the United States was Joe Biden, but after 2025, it's Donald Trump. So if we want to keep a large language model up to date, we cannot just retrain from scratch every time. That's computationally prohibitive. So we need targeted surgical edits, but what makes a good edit? We have 3 criteria. The first is the efficacy. The edit should actually work. The model should give the correct new answer after editing. And the second is generalization. The edit should generalize to paraphrases and semantically equivalent prompt, not just the exact training sentences. And the third is the locality, and it's about unrelated knowledge should remain untouched. We don't want to affect other knowledge. MEMATE is a method designed to satisfy all 3 of these criteria at scale, and let's look how it works. MEMATE is built on a key insight about transformer architecture. MLP layers in transformers function like key value memories. When a subject token passes through an MLP, it acts as a key that retrieves an associated value. The factual knowledge stored in those weights, editing then becomes a weight update problem. We want to change the MLP weights from W0 to W1 so that a given key maps to a new value, the updated fact, while preserving all existing mappings. The weights update itself has a closed form solution, which makes the MEMATE both efficient and scalable. And MEMATE does this in 2 sequential phases. The phase 1 is compute targets. For each edit, we compute a hidden state vector that represents what the model should output for that fact, and think of it as finding the target activation that encodes the new knowledge. And phase 2 is right to the weights. We then distribute this target across several MLP layers using a closed form weight update rather than modifying just one layer. MEMATE spreads this edit across multiple layers, which improves robustness to localization errors and allow batch editing for thousands of facts simultaneously. And now we come to the central problem that motivates our work. Do MEMATE edits survive subsequently fine-tuning? Here's what we mean. Suppose we use MEMATE to successfully edit 100 facts into GPT-J. It's a 6 billion parameter model, and the edit success rate is 100%. After editing, the model can correctly answer all 100 factual queries. But now, what happens if we subsequently fine-tune the model on some unrelated dataset? This is a realistic scenario because in practice, large language models are continually adapted via supervised fine-tuning for new downstream tasks. And before answering this question, we need to figure out a measurement question. Let's use this example about the Eiffel Tower is located in Paris, and we want to change it into Eiffel Tower is located in Rome. According to the behavior of fine-tuned model, we have three metrics from linear to district. The first is the added success, the ES. ES compares the probability between the target new, Rome, and the target two, Paris. And the second is the loose retained, and the LR asks the target new appears in the first 10 generated tokens of free-form generation. And the finally is the added accuracy, we short for EA, and it is an Argmax matrix. It asks to only when the only retain, well, the added only retained when the top one prediction is equal to the target new, which is Rome. And let us return to our experiment with editing on multicultural fact with GPT-J and fine-tune on the SRE first 1,000 data set. What happened? We illustrate the four matrix curves within different learning rates. This green dot lines is that the training accuracy, and the other three line denotes the three metrics we mentioned before, the ES, LR, and EA respectively. And the x-axis is the fine-tuning training steps. The first observation is about the green line. It's convergent with 15 steps, and meaning the model memorized the fine-tuned training set. And at the same time, you notice that the other three lines, ES, the green line, and EA, the red line, and the LR, the blue line, it indicated that the added retention degrades with learning rate. All these retention metrics decrease as the learning rate increases, but at different rates. This matters because once an edited model is released, downstream fine-tuning is out of our control. The higher learning rate means more aggressive overrides of edited knowledge. And about this question, our answer is edits are fragile under downstream fine-tuning, and how fragile depends on which lens you use, such as ES, EA, or LR. And next, we want to discuss, does fine-tuning erase edited knowledge indeed, and how does it do that? About this question, we have two key observations which narrows down where these failures actually lives. The first is the added signal survives in parameter space, and second is the reverting downstream layers recovers edits more effectively than reverting the editing layers themselves. For the first observation, we define two diagnostic quantities. The first one is the key drift. Key drift measures how much the input representation to the editing MLP has shifted. And second is the signal error. Signal error measures the fraction of this shift that actually couples with the fine-tuning weight updates delta W to perturb the readout. If fine-tuning erases the edit, the signal error should align with key drift well. And now let's see the results. The figure A shows that the two quantities diverge sharply as the learning rate 6E minus 5. The key drift averages about 66% across edit layers 3 to 8. Yet signal average only 17%, and the gap is this shadowed region indicates that the delta K lies predominantly in the null space of the delta W and produces a negligible change in the MLP readout. And furthermore, this figure B shows a cosine similarity remains a cosine similarity here. We give the delta W and minus K between the editing model and the fine-tuning models. We calculate its cosine similarity to denote the key vectors angle between and before and after the fine-tuning weights update. For this figure B, we show that the cosine similarity remains about 99% on every layer, confirming that the edit signal direction is preserved almost exactly, and with only a mild attenuation in magnitude. This pattern holds across all learning rates tested, and fine-tuning moves the keys, but delta W is largely blind to this movement. The edit as a parameter space object is still there. Thus, it is hypothesized that what causes the edit accuracy collapse lies not in the edited layer themselves, but in how the model decodes the preserved signal into the final prediction. For the second key observation, we use a sliding window MLP restoration tool. For each 6-layer window L plus 5, we replace the post-fine-tuning MLP outputs in that window with their pre-fine-tuned, the edited counterparts at the relevant token positions, leaving all other layers untouched. And for this figure, we show that edit accuracy recovery curve across reversion window for 2 different edit methods, mammoth and alpha edit. The key observation here is that reverting the editing layer, the layer 3 to layer A, is not the optimal for edit recovery. Instead, recovering the layers immediately downstream of this edit region achieves substantially better results. We can see the peak is in the layer 6 to 11 and the layer 8 to the 14th, but actually we just edit the layer 3 to layer 8. So I think this is the most interesting part of this work. And naturally, we want to know if there is a solution to mitigate or alleviate this robustness problem about knowledge retention. And we try to figure out it with the model interpolation techniques. And our intuition here is the edit and fine-tuning modifying largely non-overlapping parts of the weight space because the delta W is untouched and the signal preserved only the downstream readout was retrained. So if the 2 updates don't seriously conflict, a linear interpolation can preserve both, I think. Therefore, we provide model interpolation with different alpha trying here. Also reports the train accuracy and the 3 retention metrics at the same time. And the good news is that the trade-off is non-linear accuracy, edit accuracy, which is EA, and the SRE train accuracy do not decline as mirror images of each other. EA recovers quickly as alpha grows from 0. Even a small weight on the W edited restored most of the edit, and the SRE train accuracy stayed high until alpha grows large, and fine-tuned knowledge is robust to small amount of editing mixing. And that's all. Let me give a small conclusion of this work. We found that the fine-tuning can erase the edited knowledge and analyze why it happened, also give an alleviate method. For an online takeaway, one live takeaway is that edits don't fail because they get overwritten. They fail because the rest of the network forgets how to rate them, and that is recoverable. And thank you again for your listening.